Ah! Okay. 8 a.m. You're making 8 in the morning now? Yes. Yes. Yeah. Not do that? Yeah. Okay. Well, let's. Okay. So, exam 5 is Wednesday, the 15th. At 8 a.m. It will not take anyone more than 2 hours, but yeah, let's start it at 8. So it's a compromise. So yes, if you want to come at 9, you can come at 9. I don't mind staying here. It will take most people less than 90 minutes. It'll be a little longer than the other tests, but I'd say, 50% longer or something. So most people will be done in an hour and a half. Some people will be done in 45 minutes. Nobody will need more than 2 hours. And I still owe you exam 4. I will get that back to you Friday for sure. All right. Yes. Yes. I thought at first I thought you meant like after I grade the exams, will I bring them here? That'd be funny if I just graded them and didn't bring them. But okay, that makes more sense. So we are not going to go through all of mechanical vibrations. I do want to just talk about one more topic with mechanical vibrations and sort of see how that plays out. We're not going to get into forced vibrations or damped vibrations. If you want to look at that stuff, just find the playlist from last spring, and we talked about it, and you can learn a little bit about it from that. Or if you want PDFs from last year, I can give you those. Well, they're already on D2L, so the PDFs, if you look at the old lecture notes, there's stuff on it, but we're not going to get to it in this class. Does anyone have any homework questions? Yes. Okay. Okay, so that is the one that, so spring mass. Well, this is in the sections on mechanical vibrations. And it kind of just asks you to recreate what I did in class last time. So it's a mass hanging from a vertical spring, right? That's right, isn't it, Ellie? And what's the mass? Does it give numbers for all these things? Okay, and what's the spring constant? Newtons per meter. And we want to calculate the position as a function of time. And so we'll first start by saying so we want to find y as a function of time. and then we want to find the frequency. So the thought process on this just follows the derivation I did for general things before. So first, we'll do a free body diagram in the static case. So this is at equilibrium, and we're going to call y equals 0 the equilibrium position of the mass. And so the free body diagram looks like this. We have a force pulling this way of the spring constant times how much this is deviating from the resting length of the spring. Well, if you think about the equilibrium position is, so let's see, the equilibrium position is here. The mass is here when the spring is at its resting length. Okay, and so the distance between the position at the resting length and the equilibrium position is, if we choose our y equals 0 at equilibrium, it's just stretched down an amount that's equal to the distance between the resting length and the equilibrium, right? And so we can just think of, so if y0 is the mass position at the spring's resting length, that's a positive number, right? And so we can think of this tension as just equal to 500 y0. And then the weight force is 2 times 9.81, 19.62. Yes? Okay, so we're doing this step first just to come up with a relationship between the spring force at y sub 0 and the weight. Okay, so first we're doing it in the static case, and then we're going to do the motion after. Okay, so Newton's second law says 0, 500 y0 plus 0, negative 19.62 is equal to zeros because this is equilibrium. And so 500 y0 is equal to 19.62. Okay, we could use that to calculate y0, but I'm just going to set that aside for now. And now we're going to consider the general case. So free body diagram for a general location y of the mass. So we have still a downward force of gravity, 19.62. And we have a tension force that's equal to the spring constant times, and now we have to be careful here. If this y is a positive number, okay, this mass is up, right? And if the mass is up, the change in length of that spring from its resting length is negative, okay? So if we have a positive value of y, we have a compressive force from the spring, a spring force pushing against it, okay? And so we can do this two ways. We can draw the arrow downward and write it as the spring constant times y minus y0, or we can do it like this and use a negative number. But one way or the other, you have to treat the fact that if the position is a positive y, you have a compressive force on the spring, and if it's a negative value of y, you have a tension on the spring, okay? So y minus y0 and so Newton's second law says negative 500, this is the y component, so negative 500 times y minus y0 plus 0, negative 19.62 is equal to, this time there is an acceleration, so we have a mass of 2 and an acceleration 0a. And the y equation says negative 500y plus 500 y0 minus 19.62 is equal to 2a. And the reason we did that static case before we did this case is that 500 y0 we figured out is equal to 19.62. So this 500 y0 is positive 19.62, and that means that cancels with that. And you end up with y double dot plus 500 divided by 2y, so 250y is equal to 0. Because this a is y double dot. And the solution to that is y as a function of time is equal to a times the sine of the quantity square root of 250 times time plus phi. And then, did you say it says something about how you pull? So at time equals 0, y is equal to 0.01 and y prime is equal to 0. Y prime, y dot, this should say, this is the time derivative. So y dot equals 0 says that it starts at rest. Y equals positive 0.01 says that it's released 1 centimeter above the equilibrium position. And so now you can use those as boundary conditions. Let's see. So you know that when time is equal to 0, y is equal to 0.01. So 0.01 is equal to a times the sine of phi. And and y dot is equal to a times square root of 250 times cosine of phi, and the boundary condition says 0. Well, okay, well, I sort of combined these two things. So this y dot function should be a times square root of 250 times cosine of the square root of 250t plus phi. And so then when you plug in t equals 0 to get the boundary condition, you get that 0 is equal to a times square root of 250 times cosine of phi. And now you have these two equations for two variables, and you can solve that system. So let's see. Let's make let's choose phi to be equal to pi over 2. Because then we don't have, if we didn't choose phi equal to pi over 2 or 3 pi over 2 or something like that, we'd have to set a equals 0. We don't want that. Okay, that would be a trivial solution. The whole thing would go away. So choose phi equal to pi over 2. That satisfies this no matter what a is. And then, so now go to this one. Sine of pi over 2 is 1. So a is equal to 0.01. And so you get y as a function of time equal to 0.01 times sine of the quantity square root of 250t plus pi over 2. And then the frequency is just equal to 1 over 2 pi times square root of k over m. So that's square root of 250 over 2 pi, whatever that is. $15.5. Yeah, can you calculate that for me? $2.52 hertz. Is that the unit you want? Yeah. That's 1 over seconds. For the first answer, y to t, would you accept 101 cosine with? Yes. Square root of 250. Yeah. Any other questions about that one? Yes. Mm-hmm. Would it always be like this simple where you can see like, oh, I don't want. Yeah, right. So yeah, you're going to have these two equations, You definitely know that you don't want A to be equal to 0 because then your solution is just 0 for all time. That's the trivial solution. So find a solution that solves for one of them without having to restrict A. And then second, go back and find A from that. And by the way, you could have chosen, I could have chosen B equal to 3 pi over 2. And then when you plug that back in here, you would have had sine of 3 pi over 2, which is negative 1. And then you would have gotten an A that was equal to negative 0.01. So your solution would have been y is equal to negative 0.01 times sine of square root of 250t plus 3 pi over 2. It's a different solution, but it looks the same. The graph is the same and everything, so that's fine. Yeah.
You set the y of 0 force equal.
Yeah.
When you set it equal the force of the actual, that should represent equilibrium.
So this part where I'm crossing out 500y0 and yeah. Okay, so the first thing I did, and this is just something you have to remember to do problems like this. The first thing I did is I did a static case. And in the static case, I figured out that 500y0 is equal to 19.62. And so from that point on, we know that anytime we see 500y0, we can replace it with 19.62. That's the reason we did the static case, because I happen to know that in the next step, we're going to have this extra term of 500y0 that I'm going to want to cancel out with a 19.62. Okay. But I'll tell you what, I will not do a vertical problem like this where I make you derive it in 2 steps. Like this is more than I want you to worry about right now. I won't make you do a derivation like this on the test. All I want you to remember is this. So just remember, if the springs are oriented vertically, choose your y equals 0 to choose your y equals 0 location at the equilibrium position, that hanging equilibrium position. Not at the spring's rest length. Okay. Any questions about what I'm talking about there? So if you have, like, for example, so let's say this is 5 kilograms, this is 1,000 newtons per meter, and the spring, the mass is pulled down 5 centimeters and released from rest. You can just choose y equals 0 at equilibrium. And that means that at time equals 0, y is equal to negative 0.05. Y dot is equal to 0. You know that the form of the function is this. And then just use those boundary conditions to find A and phi. So let's see, 1,000 divided by 5 is 200. Square root of 200 is so A times sine of 14.14 t plus phi. And now you're just using the boundary conditions to get this function. So at time equals 0, y is equal to negative 0.05. So that's one equation. Y dot is equal to 14.14 A times cosine of the quantity 14.14 t plus phi. And so the second boundary condition says 0 is equal to 14.14 A times cosine of phi. So again, I mean, I guess it's always the case that if the thing is just pulled to a location, pushed to a location, or put in some fixed location, released from rest, you can always use phi equal to pi over 2, because it's just going to be a cosine function. And so phi is equal to pi over 2. A is equal to, in this case, negative 0.05. And so y as a function of time is negative 0.05 times sine of the quantity 14.14 t plus pi over 2. The period is 2 pi times the mass over the spring constant, square root. Can you tell me what that number is? .0705 seconds. And the frequency is 1 over the period. What's that? Oh, okay. 0.444 seconds, and then what's 1 over 0.444? 2.25 hertz. So 2.25 oscillations per second. The approach for a horizontal thing, frictionless horizontal thing, oscillating like that, it's the same approach. It's just that your zero position is at the resting length of the spring, which is also the equilibrium position. Any questions about that one? Okay, well, yeah. What? The resting length, for a problem like this, you don't even need to know what it is, but if you wanted to calculate it, do it in a static case where you know, let's say, so what are we going to calculate here? What's the amount the spring is stretched at equilibrium? Okay, so you can, a free body diagram at equilibrium looks like this. You have KY0 pulling up and a weight force pulling down. And Newton's second law says 0 K times Y0 plus 0 negative mg. And since it's at equilibrium, this is equal to 0. So KY0 is equal to mg. So Y0 is equal to mg over K. So that's how far above the equilibrium position the rest length of the spring is. And it makes sense, the more massive it is, the bigger the more the spring is stretched at equilibrium, and the stiffer the spring is, the less it's stretched. Okay, well, there's just two more things I want you to know. I don't know if I really have time to go through derivations of these, but so springs in series and parallel. So a series spring is like this. So you have one spring there connected to another spring. Call this one K1 and this one K2. Okay, you could wrap duct tape around that. No, that would affect the way they work as springs, but you could put some kind of opaque coating around this and sell it as a single spring. That's not a very good business model because you pay for two springs and sell it as one. But for calculations, it's useful to just be able to represent this system as a single spring. Okay. How would that? So to treat this as a single spring, with the spring constant K. 1 over K is equal to 1 over K1 plus 1 over K2. For the people who are taking circuits, it's like the series and parallel relationship is opposite of what it is for resistors. I guess it's the same as it is for capacitors, though, isn't it? And for parallel springs, if you have a K1 and a K2, to treat this as a single spring, with a stiffness of K, K is just equal to the sum of K1 and K2. Okay, so for example, what's the frequency of a 1 degree of freedom system? So we're talking about a system that only moves in a line. So we're not worrying about this thing starting to rotate back and forth or anything. And let's say the setup is like this. Okay, so you have a spring with a constant of 200 newtons per meter. Connected to another one where you have a 100 Newton per meter and a 300 Newton per meter, and it's connected to a mass of 1 kilogram. So what would be the frequency of that system? Well, you can just one by one treat the parallel springs as a single spring, and now you have 2 springs in series. Treat those as a single spring, and then just calculate the frequency the same way you would if it was a 1 spring system. So this is the same thing as this system, where this one is 200 newtons per meter. And 2 springs in parallel, the stiffness is just equal to the sum. So that's 400. And now this is equal to a system with a single spring, and we can calculate K as, so 1 over K is equal to 1 over 400 plus 1 over 200. So 1 over K is equal to 3 over 400. And so K is equal to, I think that's 133.3 repeating. And so the frequency of this system is 1 over 2 pi times the square root of 133.3 repeating over 1 kilogram. And what does that come out to numerically? 18? Okay. 18 point. Really? That,
137.
square root of 133 is, okay, 1.84, because it's like a little over 11 divided by 6. So this looks about right. So any questions about that? So that's how you can reduce a complicated system of springs in this case to a single system, and then it's easy to fit it into the mathematical stuff we've done. Yep. Yes. Anytime you could do it in degrees until the point that you want to take time derivatives of that function. Could you, I don't think that's true either. I think it needs to be in radians no matter what you do with it. But mainly in dynamics, like anytime you have functions of time that involve sine and cosine functions, trig functions, you need to have your stuff in radians because we're taking a lot of derivatives, and derivatives don't work with trig functions unless it's in radians because of the chain rule. Any other questions? Okay, so what should you know how to do for vibrations? First, you should know how to find, so use the boundary conditions to find A and phi in the function A times sine of the quantity square root of k over mt plus phi. Find the frequency and period. And I'll give you those expressions so you don't even have to remember that. And then simplify systems with series and parallel springs. Yes. Yes. Mm-hmm. That is. Yep. So if you have, yes, they still add together. Yep. It works just the same way. Those are in series, and it works like that. They don't add together. Sorry, the relationship is the other one for series. 1 over k is equal to 1 over k1 plus 1 over k2. Parallel is the one where you just add the constants. Any other questions?
Scroll up again.
Yeah. Okay, that's all.